Hello everyone, today we will present our review paper on reliability analysis in file systems. We will compare two fundamental approaches, journaling file systems and log-structured file systems, examining their reliability, performance and use cases. Our presentation consists of 6 main sections. First, we'll explain why this topic is important. Then we'll introduce the base concepts and examine both file system approaches in detail. Finally, we'll complete with comparative analysis and recommendations. What happens if power is lost during a file system write operation? When the operating system creates a file, it performs multiple disk writes, allocating an inode, updating the bitmap, creating a directory entry. If any operation is interrupted, the file system enters an inconsistent state. The traditional solution, FSCK, scans the entire disk to detect inconsistencies. However, for large disks, this can take hours, unacceptable for systems requiring high availability. Two approaches have been developed to solve this problem. The journaling approach writes change to a separate log region first. If a crash occurs, the system reads this log to replay completed operation. The log-structured approach writes all changes sequentially to unused disk areas. The disk behaves like a continuously appending log, particularly efficient for SSDs. The fundamental principle of write-ahead logging is simple. No change is applied to the main data structures without first being written to a persistent log. If a crash occurs, the system only checks the journal on restart. It identifies completed transactions and replaces them, discards incomplete ones. This way, the file system returns to a consistent state within seconds. This principle also forms the foundation of database systems. ext4 is the most widely used Linux file system, performing journaling through the GBD2 layer. The journal is a circular buffer containing 4 block types. Descriptor blocks specify which file system blocks are logged. Data blocks hold actual content. Commit blocks mark transaction boundaries, and revocation blocks indicate blocks not to replay during recovery. Each transaction goes through 4 phases. Running accepts modifications, committing writes to journal, checkpointing transfers to main storage, and forgotten reclaims journal space. ext4 offers 3 journaling modes with different reliability performance trade-offs. In data journal mode, both metadata and file data are journaled. Most secure but doubles writes. The default mode, data ordered, only journals metadata but guarantees data blocks are written before associated metadata is committed. This prevents old deleted data from appearing in new files. Data write back is fastest but risky. After a crash, old data may appear in newly written files. In 1991 at Berkeley, Rosenblum and Osterhout introduced the log-structured file system concept. Their key observation: as memory sizes grow, most reads are served from cache, and disk traffic becomes write-dominated. Traditional file systems do random writes, so due to SIG overhead, they only use 5 to 10% of bandwidth. LFS solution is radical. Buffer all changes and write them to disk as a single large sequential write. The disk behaves like a continuously appending log. This increases bandwidth utilization to 70%. F2FS is a log-structured file system developed by Samsung in 2012, specifically optimized for NAND flash storage. F2FS contains 6 areas. Superblock holds partition parameters. Checkpoint stores file system state in 2 copies, critical for crash recovery. SIT and NAT hold segment and node address information. SSA contains owner information for garbage collection. The main area organizes actual data in 4 kilobytes blocks within 2 megabyte segments. An important innovation is writing hot, warm, and cold data to different logs, improving garbage collection efficiency.
The biggest challenge of log structure systems is garbage collection. As data is updated, old versions become invalid, but still occupy disk space. The garbage collection process works like this. The system identifies segments with many invalid blocks, copies still valid data to new segment, and completely deletes the old segment. F2FS uses the two garbage collection types. Foreground garbage collection works synchronously with the greedy algorithm when space is urgently needed. Background garbage collection runs opportunistically with a cost-benefit algorithm. However, garbage collection has a significant cost: write amplification. You may write same data multiple times. This ratio typically is about 2.5 times in F2FS, reaching up to 10 times in worst cases. This comparison shows that fundamental difference between two approaches. In journaling, the write request first goes to the journal. After transaction commit, it's written to main storage through checkpointing, a two-stage process. In log structured, the write request accumulates in memory buffer, then writes to disk sequentially as a segment. Index tables are updated. Garbage collector cleans old data in background. The key difference is journaling focuses on metadata consistency, while log structured optimizes an entire write pattern. Both approaches provide fast recovery after a crash, but their mechanism differs. In X4, when system restarts, the journal super block is read, all transactions are scanned, transactions with valid comment records are replayed, those without are discarded. In F2FS, both checkpoint copies are read, the valid one is selected by version number. If there is a fsync data after the last checkpoint, roll forward recovery applies it. In both approaches, recovery time is seconds, regardless of disk size, a massive improvement over hours-long FSCK. This table summarizes reliability metrics of both approaches. The Crash Monkey and ACE framework tested these file systems for 5 years and found only 2 bugs in each, demonstrating both implementations are very mature. Recovery times are seconds for both. However, there are important differences. In write amplification, X4 has clear advantage, 1.122 times versus 2.5 times to 10 times in F2FS, directly affecting SSD lifespan. In HDD performance, X4 is optimized for, while F2FS performs poorly due to random reads. On SSDs, F2FS can be up to 3 times faster. In online warfare, E2FC is much more powerful and reliable. Write amplification means writing more data than what actually needs to be written. X4 in ordered mode does only 1.2 times extra writes, while journal mode goes to 2 times. F2FS is more complex. Typical usage is around 2.75, but when garbage collection is intensive, it can reach to even 10 times. Why does it matter? NAND flash cells SSDs can only handle a limited number of writes. Higher write amplification means faster SSD wear. This metric is critical, especially for write-intensive systems. Storage medium is critical for file system selection. On HDDs, sequential access is 100 to 200 megabytes per second, while random drops to 0.5 to 1 megabyte per second due to seek time, a 200 times difference. This gives journaling file systems an advantage. X4 batches metadata updates and keeps long journal continuous to minimize seeks. F2FS performs poorly on HDDs because log structured reads require many seeks to scattered locations. On SSDs, there is no seek penalty, so random and sequential difference is much smaller. F2FS sequential writes patterns aligns perfectly with flash erase before write requirement. Benchmarks show that F2FS is 2.1 times faster in random writes and 2.5 times faster in fsync operation on flash. So which file system for which situation? For enterprise servers and databases, we recommend X4 over 15 years of proven reliability, robust UTF-CK repair tool, and proven crash consistency. For mobile devices and Android, F2FS is more suitable. Manufacturers like Google Pixel, Samsung, Huawei, and OnePlus prefer F2FS for its flash optimization and superior write performance. For desktop systems with SSDs, both are acceptable depending on workload. However, in environments with frequent power failures, X4 should be definitely be preferred. FCCK.F2FS has known weaknesses. Before concluding, a critical warning. Neither X4 nor F2FS provides checksums for file data. Both protect the metadata. inodes, directory structures, allocation bitmaps are checksums. But file content itself is not protected. What does it mean? If silent bit corruption occurs on a disk, it's common on older disks and large storage systems. The file system cannot detect it. Your data may be corrupted without you knowing. If data integrity is critical, consider file systems with data checksumming like B2RFS or ZFS, or implement application double checksums. In conclusion, both approaches are successful in their respective domains. X4 with over 15 years of production experience is trusted by enterprise world. Its robust repair tools and HTTP optimization make it ideal for servers. F2FS reflects the realities of the flash storage era, up to 3 times performance improvement on SSDs and sequential write patterns make it the choice for modern mobile devices. As CrashMarket has shown, both are mature and reliable implementations. There is no single correct file system. The right choice depends on your storage medium, workload patterns, reliability requirements, and so on. These are the sources we used. These are the only main sources we used. We have other ones in our paper. The FS paper by Rosenblum and Ostrad and the F2FS paper by Samsung are fundamental works in this field. The CrashMarket framework is a groundbreaking tool for testing file system reliability. These are our emails. You can contact us if you have any questions.